The journey of offshore wind turbines began in 1991 with the first farm in Denmark, producing 450 kilowatts. By 1996, a subsequent project showcased turbines with a 500 kilowatts capacity, marking significant progress in a time of widespread skepticism about offshore wind's potential. Today, offshore wind technology continues to advance rapidly, with 2030 and its target deadlines on the horizon. Let's explore the latest developments driving the industry forward. Bigger and more powerful turbines. The demand for larger turbines with higher capacity factors is pushing the industry to develop record-breaking machines. GE's Haliade-X set a new standard with a 13 megawatts capacity. However, the prototype Goldwind GWH 252, 16 megawatts, has already surpassed this, breaking the record for most power produced in a day. Meanwhile, Mingyang Power is planning even larger turbines, with 22 megawatts and 18 megawatts models in development, indicating that Goldwind's record will be short-lived even before it reaches commercial production. Enhancing turbine materials. As turbines grow larger, the materials used must withstand greater stress. One solution is carbon fiber composites, which offer superior tensile strength and are lighter than traditional fiberglass polymer blends. Additionally, the use of additive manufacturing, 3D printing for components, is gaining traction. According to a study by the National Renewable Energy Laboratory, additive manufacturing can produce high-performance blades that are longer and more cost-effective, despite challenges related to material strength and initial costs. Floating wind, the next frontier. Floating wind technology, though still in its infancy compared to fixed installations, is rapidly advancing. Despite its early stage, floating wind is projected to contribute up to 5% of offshore wind's 2030 targets. Rapid development is necessary, with over 120 floating wind designs currently on the market. Companies are adapting ports to handle the larger, heavier components of floating wind systems, with innovative approaches such as building substructures on modular dry docks that can be towed to installation sites. The next few years will likely see consolidation as companies seek the most cost-efficient configurations. Optimizing maintenance with AI. Traditionally, wind turbine maintenance schedules are based on manufacturer specifications, with inspections occurring annually or biannually and corrective maintenance performed as needed. Offshore turbine maintenance is particularly challenging due to the difficulty of moving crews and equipment to sea, necessitating specialized vessels booked well in advance. Unpredictable weather can further complicate this process. AI and machine learning offer a solution by enabling proactive and efficient maintenance. For example, researchers at the Korea Institute of Energy have developed an AI model capable of predicting component failure with up to 90% accuracy. Robotics, revolutionizing operations. Robots have played a significant role in offshore wind, initially through remote-operated vehicles used for building offshore farms. ROVs continue to inspect turbine foundations, seabed topography, and cabling, areas too risky for human divers. In the near future, robots are expected to take on even more tasks, including those above sea level. Robotics expert Yvonne Petillot of Heriot-Watt University predicts that within 5 years, human inspections on offshore turbines will be replaced by robots like the blade bug, a 6-legged robot designed to assess and repair damage. Meanwhile, the amphibian robot will handle tasks such as cleaning biofouling and assessing structural damage in typically inaccessible areas. Despite recent challenges such as rising costs and supply chain issues, the offshore wind industry remains committed to technological innovation. From record-breaking turbines to AI-driven maintenance and advanced robotics, the next decade promises unprecedented advancements in offshore wind technology.